Let's move on. Okay, so we were discussing about the Fourier series and Fourier transform. Let's discuss it more.
Okay.
Yeah. Okay, so let's say Fourier series representation of periodic signal. So how you can represent a periodic signal in a Fourier series. So let's xt be a CT periodic signal, that means continuous time periodic signal period. X of t plus t is equal to x of t. That is the shifting. How that is the period. Okay, t, this capital T. How much you will shift. Okay, so let's say this is a periodic signal. Had t is equal to 2. See the period. Let's start from the 0. Come here. That's 2. That is the period. So periodic signal with fundamental period t is equal to 2. So that is the period of here of this signal. Example, the rectangular pulse train. This is a rectangular pulse train. Start from here minus 0.5 to 1.5. So the range would be 1.5 minus 0.5. So then it would be 2, right? That is the range of the period. So period is that 2.
Okay.
Okay. Then xt can be expressed as, so then xt can be expressed as k is equal to minus infinity to infinity c k e j k omega naught t. Okay, c k e to the power j k omega naught t. Omega naught is the angular frequency. K is a constant. See, k, the value of the k changes from minus infinity to infinity. Okay, any real value, in any real number it could be. Where omega naught is equal to 2 pi over t is the fundamental frequency of the signal. So omega naught is the fundamental frequency or angular frequency. Actually, we know that it is the angular frequency 2 pi f, right? We know the omega is equal to 2 pi f, right? 2 pi f. So, or we can write it like this: 2 pi over t. That is the omega, right? Or the angular frequency. Okay.
Yes.
Okay. So it is called the fundamental frequency. Remember, this is the uh, equation. Okay. This is the equation of Fourier series. Okay. Any equation you would like to express like this. Now, so ck, so if we break this one, so we can write the 1 over t minus t by 2 to the t by 2 x of t if you want to write this, okay, x of t e minus, then this will go there, right? Minus j k omega naught t dt, integration, it will be integrated. Okay, this is the value of ck. Okay, instead of ck you can write this one. Okay, so here k, range of k 0 plus minus 1 plus minus 2. C naught is called the constant or DC component of xt. C naught is called the DC component of the xt. We already have seen that in the last class. Okay, so a periodic serial xt has a Fourier series if it is satisfies the following conditions. Some conditions are there, like xt is absolutely integrable over any period. So you can integrate xt over any period. xt has only a finite number of maximum minima over any period. Finite number of maximum minima should be there. xt has only a finite number of discontinuities over any period. A finite number of discontinuities over any period. Okay, let's see here from figure. t is equal to 2, t is equal to 2, so omega naught 2 pi by 2 is equal to pi, right? Clearly, xt satisfies the Dirichlet conditions and thus has a Fourier series representation. So it represents it sees it satisfies this condition xt. So it is a range, right? Finite range over any period, namely has a finite number of minima, finite number of discontinuities. Period is 2, t is equal to 2, so omega naught fundamental frequency 2 pi by 2, it would be pi. The value of pi is what? 180 degree, right? So 180 degree. So clearly xt satisfies the this for conditions, and it is a Fourier series representation. Okay, and see rectangular pulse train. These are the pulse train. Line is spectra for the rectangular pulse train. These are the pulse train. 0 value is half pi, 1 over pi. Like this. This is also line spectra for the rectangular pulse train. Okay, trigonometric Fourier series. So Euler formula we can rewrite. By using the Euler formula, we can rewrite this. This is called the disk component. This is the kth harmonic. You also have learned the kth harmonic. As long as xt is real, it satisfies. This expression is called the trigonometric Fourier series of xt. So this kind of equation called the trigonometric Fourier series of xt. Okay. Can be rewrite the equation can be rewrite as like this. Okay. Given an odd positive integer n, define the n partial sum of the previous series. We have seen this in the last class. According to Fourier's theorem, it should be the limit n tends to 0. Okay. Parseval's theorem. Okay, see this. Let xt be periodic signal with period t. Okay, the average power P of the signal is defined as this is the average power. This is the Parseval's theorem. That is the average power of T, xt, 1 over T minus T by 2 into the range of integration is minus T by 2 to the T by 2 x square T dt. And the expressing the signal xt, so we can write the xt like this. Okay, then here we can write the this one ck square. Okay, so we can write like this. Okay, now come to the Fourier transform. That was the Fourier series. We have seen that periodic signals can be represented with the Fourier series. Can a aperiodic signal be analyzed in terms of frequency components? Yes, and the Fourier transform provides the tool for this analysis. See this. For the periodic signal, we will use the Fourier series. For the aperiodic signal, we will use the Fourier transform. The Fourier transform provides the tool for this analysis. Okay, so the major difference with respect to time, W or T means with respect to. The line spectra of the periodic signal is that the spectra of aperiodic signals are defined for all real values of the frequency variables omega naught, just for a discrete set of values that are defined for all real values. It is defined for all real values. Okay. Fourier spectra of aperiodic signals are defined for all real values of the frequency variable, not just for a discrete set of values. Okay. So xt, see this, this is the xt, and the limit x of t tends to infinity. Okay, plots of the 1 second rectangular pulse and pulse train. That is the 1 second rectangular pulse. That is the pulse train. Okay, since xtt is periodic with period t, we can write it is a periodic. So you can write this. So what would be the ck? This one. What happens to the frequency components of x of t as t tends to infinity? For k is equal to 0, if I put the k is equal to 0, then c naught is equal to 1 by t. For k equal to plus minus 1 plus minus 2, it would be ck 2 by k omega naught t sine this value, where omega naught is equal to 2 by t. Okay, that is the equation of ck. Now you put the value of k, then you will get the values. Okay. They plot frequency content of the rectangular pulses. So plots of t of ck, where omega is equal to k omega naught, is just put the values of t, different values, 2, 5, 10. Okay. That is one kind of, that is another kind, that is another kind. At first t is equal to 2, here put the value t is equal to 2, here put the value t is equal to 5, here put the value t is equal to 10. Then you will get the equation. Then you will get the pulse train like this. Okay, spectrum, scale the spectrum like this. So using the MATLAB, you can plot this kind of figure easily, just using the equations. Okay, so we can show the equation. So show the wave or xt for the different values of t, like here this is the k omega naught radian per second, and here it is the amplitude. Okay. So tck, amplitude versus frequency plot. Okay, it can be easily shown that limit of t tends to infinity, t of ck sin omega by 2 pi, where sin k function lambda is equal to sin pi lambda by pi lambda. Okay, you can use the MATLAB for these plots. The Fourier transform of the rectangular pulse xt can be defined as to be limit, that is the limit tck sin omega by 2 pi omega. Okay. General case, given a signal xt, its Fourier transform x omega. So let's look at the general term. A signal xt, the Fourier transform of that. Okay, that is the general equation. This equation is the general equation. Okay, x of omega is the Fourier transform. It is the Fourier transform of xt. Okay, so minus infinity to infinity x of t e minus j omega t dt. Okay, like this. A signal xt is said to have a Fourier transform in the ordinary sense if the above integral converges. Okay, so remember this equation. This equation will be required. Okay, the integral does converge if the signal xt is well behaved. Xt is absolutely integrable. That means xt should be integrable. Okay, minus infinity to infinity x of t dt less than infinity. Not well behaved means that the signal has a finite number of discontinuities, maxima and minima within any finite time interval. So that means the well behaved. Okay. The constant signal. Let's consider the signal x is equal to 1. Clearly, xt does not satisfy the first requirement since infinity. Therefore, the constant signal does not have a Fourier transform in the ordinary case. C. The constant signal does not have a Fourier transform. But in a general sense, it has a value. Consider the signal exponential. Okay, so at first we have considered the signal xt is equal to 1. Let's consider the xt is equal to e to the power minus bt ut. So now what would be the Fourier transform is given as infinity to infinity. Okay, e to the power minus bt ut e. So that is the value of xt. Now what will happen? E, we can write minus bt plus j omega t, right, dt. Now if we integrate this, then this will be the result. If b is less than 0, see, if b is less than t, the value of t 0 to infinity, that means infinity minus 0. If b is less than 0, x omega does not exist. If b is equal to 0, xt is equal to at, and x omega does not exist either in the ordinary sense. If b is greater than 0, it is x omega 1 over b plus 3 omega. Okay. So if b is higher than 0, then it will exist. It will exist. Okay. Otherwise, it will not exist. So x omega would be 1 plus b, 1 divided by b plus j omega. So amplitude spectrum. So what would be the amplitude of this one? 1 by square root of b square plus omega square. And phase spectrum argument x omega by b. That is the formula. Okay. So amplitude and phase spectra of the exponential signal. So that is the frequency and that is the x. Okay, 0.1 like this. Plot of the amplitude and the phase spectra. So that is the amplitude and this is the phase spectra. Okay. Consider this one. X omega minus infinity to infinity x of t e to the power minus j omega t dt. Since x omega is in general is a complex function, by using Euler theorem we can write this. So using the Euler theorem we can write like this, because do you remember this equation? E to the power minus j theta is equal to cos theta minus j of sin theta. That is the Euler formula. So they have applied this one minus. See, here comes a minus. Here comes a minus. Because they break it down. They break it down cos omega t minus sin omega t. Instead of theta, they use the omega t. Okay. So we can write like this. X omega, x of omega is equal to r of omega plus j of I omega. Right. We can write like this. So instead, if I break it down into the Euler formula, then we can write like these equations. Okay, r omega. Let's consider it as r omega, and let's consider it as I omega. Then I can write like this. Okay, so in the polar form, we can write like this: x omega r omega plus j I omega can be expressed in the polar form. So x omega is equal to, that is the x omega, amplitude of the x omega, exponential j argument x omega. That means where this one can be written as the amplitude and this one can be written as the angle. Tan inverse, arctan means the tan inverse. Okay. If x is real valued, see, if x of t is a real value signal, then x of minus omega, it would be conjugate of x omega. Moreover, if I write the conjugate, both are same. Okay, then like this. That is called the Hermitian symmetry or Hermitian symmetry. Okay. So consider this event signal, rectangular pulse of duration tau seconds. That is the tau second. It is x omega 2 0 to tau by 2, 0 to tau by 2 on this one. 1 value is 1. Cost omega t dt. And do the calculation. So it would be tau sinc omega tau by 2 pi. Or you can write like up to like this. Okay, now another function, sinc function omega tau by 2 pi. Returns of the tau second rectangular pulse. Okay, so amplitude spectra, phase spectra. That is amplitude spectra, that is the phase spectra. Okay, now see another one, band limited signals. A signal is said to be band limited if its Fourier transform x omega is 0 for all omega greater than b, where b is some positive number called the bandwidth of the signal. B is called the bandwidth of the signal. It turns out that any band limited signal must have an infinite duration in time. That is, band limited signals cannot be time limited. Okay, it cannot be time limited. Okay, signal xt is said to be band limited if its Fourier transform x omega is 0 for all omega is greater than b, where b is some positive number or the bandwidth of the signal. Okay. And if a signal xt is not band limited, it is said to have the infinite bandwidth or an infinite spectrum. So if it does not have any bandwidth, then it can be called as the infinite bandwidth or the infinite spectrum. Time limited signals cannot be band limited, and thus all time limited signals have infinite bandwidth. However, for any well behaved signal xt, it can be proven that limit is equal to 0. Okay. So inverse Fourier transform, it is another form. Given a signal xt with Fourier transform x omega, xt can be recomputed from x omega by applying the inverse Fourier transform. So if you have the x omega, if you find the x omega, then you can also find out the xt inversely if you have the x omega. Okay. So this is the formula for xt to inverse Fourier transform. So inverse Fourier transform, that is the equation for the inverse Fourier transform. 1 over 2 pi limit minus infinity to infinity x omega e j omega t d omega. Okay, that is the, so in that case it you can write like this. That means xt can be converted to x omega and x omega can be converted to xt. Okay, vice versa. Okay, so properties of the Fourier transform. Fourier transform, properties of the Fourier transform. Linearity. One property is linearity. Left or right shift in time. So left or right shift in time. Time scaling is possible. Shifting is possible. Time reversal is possible. Multiplication by a power of t is possible. Multiplication by a complex exponential, it is also possible. Complex exponential, right? That is the complex exponential. That is the power of t. Okay. And multiplication by a sinusoid modulation. Differentiation in the time domain. You can differentiate in the time domain. It is also possible in the Fourier transform. Integration in the time domain. So integration in the time domain is possible. Convolution in the time domain. Convolution is possible. Multiplication in the time domain. Multiplication in the time domain is also possible. Parseval's theorem. There is the Parseval's theorem. Duality. Okay. Okay, so these are the properties of the Fourier transform. See, you can check this one. These are the properties of the Fourier transform. Okay, so I have missed few things. Oh, okay. See the linearity. Linearity means see this. If you convert it to the signal example, I think this one linearity P4 P2 P4 P2. If you add these two signal, then you will get this one. This signal xt. Okay, you will get this signal, and finally you will get the result. Okay, time shift. So they gave some examples, time scaling. All examples are there. You can check. Okay, so generalized Fourier transform of delta t of e j omega t is equal to 1. So if you apply the duality property, so you get the generalized Fourier transform. Okay. The Fourier transform of periodic signals. Let xt be a periodic signal with period t. As such, it can be represented with its Fourier transform. Okay, so here omega naught equal to 2 pi by t. It is, so since you can write like this, just put this value. Since ut is equal to minus infinity to t delta tau d tau, using the integration property, just put the integration property here, then you will get the ut. Common Fourier transform pairs. So these are the common pairs. Okay. Okay, let me show you another one. What I forget to show in the previous class. Okay. This one, I think I have started this one. So periodic signal, a periodic signal. Okay. Even an odd signal, real complex, you have seen this. So any periodic power signal, in fact, sum of sines and cosines at different frequencies. That is the Fourier series. Periodic signal. Okay, so we have seen this Fourier series property. We have seen the property Fourier transform. Fourier transform, that is the Fourier transform. Fourier represents a periodic function as a continuous summation of sines and cosines. Definitions are there. Continuous Fourier transform. We want a spectral representation for a periodic signals model. Okay. Fourier analysis band limited. Say function is band limited if 0 for all frequencies. Amplitude spectrum is okay. Sometimes they show it as x or f Fourier. Okay, inverse Fourier transform. We have also seen this. Okay. Okay. So today we have discussed about the Fourier, right? Fourier series, Fourier transform. We have discussed about it. Fourier transform discrete signals. That is another term. Uh, let's move on to that. Okay, here see Fourier transform of discrete signals. See, sampling. Important term is sampling. Continuous signals are digitized using digital computers. When we sample, we calculate the value of the continuous signal at discrete points. How fast do we sample? What is the value of each point? Quantization determines the value of each sample's value. Using the quantization, we can find out the value of each sample. Okay, sampling periodic functions. Xt is the continuous time signal we use to sample. Let's say xt is the continuous time signal we use to sample. Yt is equal to xst is equal to xtpt be the sample signal. Then xst is equal to yt. So my k is equal to minus infinity to infinity x of t delta t minus kt. Okay, or we can write it like this summation. Okay. Let omega s be the sampling frequency. Let's omega s be the sampling frequency. So what is the Fourier transform of this? 1 over 2 pi x omega convolution omega s summation of k delta this one. note that WB is the bandwidth. If omega s minus omega b is less than omega b, then aliasing occurs, signal overlaps. To avoid aliasing, okay. So I will discuss it in the next class details because it is interesting thing. Sampling, okay, sampling periodic functions, discrete time Fourier transform. That is another important thing. So I think it requires a single class. Okay, some things are also there. So I will also share this slide today. I will upload this on now in your uh, Google Classroom. Okay, so it is
Sir,
important. So
hello,
sometimes,
sir.
yes,
Finish. Continuous.